doing differentiation, right? We have done sequences, limits, continuity, differentiation, and so on. But now we want to move to, because the goal is that later, maybe not today, study derivatives of complex functions from C to C, polynomials from C to C, and so on. But before that, we'll have to take, I mean, I'm sure all of you know complex numbers, right? Complex numbers. But we will try to take a closer look at them, like how we can view the complex numbers in different ways. And let's see. Yeah, let's first start with that. Yeah. And then we'll see how far we can go today. The goal is to finally understand derivatives of complex functions. It can be important in problems which don't have complex numbers to start with even. Okay. But let's see. Yeah. So let me present my screen. I have not done that. Right. Right. So just start with complex numbers. Yeah, what is this about? Yeah, so the idea is that when we start with functions from R to R, right? When we start with functions that are just defined from R to R, or let's say all the expressions in them are real, or for example, we want to prove some identity. For example, when you want to prove some identity, let's say something like this: n choose 0 plus n choose 3 plus n choose 6, and so on. Identity means, let's say you want to sum this. Then a natural place to look at is this expansion, right? This kind of expansion. Yeah. So I'm just trying to motivate the complex numbers, like, and there are some traditional ways to do that. I know, through equations, x square minus 1, x square plus 1 solution of that, and so on. But I just want to take it slightly different. So we have this identity, right? This identity we sort of prove. You could say we prove it for reals. But still, we benefit from substituting. Yeah. We benefit from substituting x equal to omega. If you don't know what that is, it's fine, but I mean, just third root of, but at least let's say x equal to I. We benefit from x equal to I minus I omega and so on, right? So this is an example of a situation where the function is from R to R, okay? I mean, you can consider this as an expression from R to R, or whatever, yeah? It's just expression from R to R. The domain is R to R, but we benefit by extending, right? By extending the domain to be from C to C. Yeah, do you all agree with this? Like, otherwise, this problem is difficult. Or I should say, the solution using complex numbers is much simpler. Right? And there are many things like these where you don't have complex numbers to start with, but by putting these complex numbers, So what are we actually doing? When you put these complex numbers, when you substitute these complex numbers, you are kind of allowing more identities, right? You're allowing more equations. In general, you're allowing more possibilities, right? You're allowing more equations which are legal. So for example, when it's from C to C, then every polynomial will have solutions, right? So you're kind of allowing more equations, more identities, and that's why you may discover more things. It can be said in other ways, like allowing more symmetries and such. So you're looking at the number line in a bigger place. Okay, you're looking at the number line in a bigger place, and that is a plane. And then you're also moving the number line and looking at it from different angles. So these are all copies of R. And that's in that way you sort of discover more about R itself. Okay, so it's definitely important to have these things, have new symbols. It's important to have new symbols. It's important to have new equations like these to be true. And of course, we define a number that does it. And then we make sure that we are able to amalgamate that number into our original number system so that we can do arithmetic, on the new number system that we get, R with the I, with a symbol that satisfies this equation, which we call I. And then the rest of the things you know, right? Yeah, it turns out. Okay. Any questions up till now? Now I'm going to be a bit more concrete. Okay. So next, what we want to see is from R2 to C. Okay. We want to see the connection between the plane and how from the plane you can go to the complex plane. Okay. What are the differences? What are the similarities and so on? What is added to go to C and why we do it is also important. So in C, in the complex numbers, so we are not being very rigorous and developing things from the very minimals and moving forward. No, we are not trying to do that. We're just trying to, we are assuming we know complex numbers, but we're just trying to understand it better and understand it from different angles. It's a theoretical, presentation. The complex numbers, they have this addition and this multiplication. We have these two things. R2 has only addition. Okay, when you view the complex numbers as R2 and on top of that you introduce some kind of multiplication, okay, then you know that the additive structure on C will just behave like R2, and everything on the complex numbers which is defined in terms of addition will just behave like what happens in R2. And that will help us to, like, that all the analysis on complex numbers not involving differentiation can be done by the what you can do with analysis on R2, and that's just same notions as R, just the same sense of distance and so on. But let's go more in details with this. So we have this R2, we have R2, we have this pairs of numbers, right? And we know how to add these things, right? So we certainly know how to add this. So this, we know these things, and I'm not going into details about what is geometric view of these and so on. Those things are quite straightforward. Yeah. But now what we want to do is solve a computational question. A computational question. There's one way to put it. Question. And the question is this. Starting, and this is a question that leads to, well, that's one way to approach, and historically this was one way in which one sect of mathematicians approached to complex, means they discovered this multiplication, which they called complex multiplication. Starting with a vector, and this is very useful for applications in, let's say, high school math and Olympiad geometry, and for elementary maths. Starting with the vector v1, let's denote it as y1. What? Okay. Where does rotation of v1 by v2, so I'll explain this, take v1 2, I'm writing it very explicitly just intentionally, take v1 2. Okay. Now what do I mean rotation of v1 by v2? Okay. Let's try to understand that. It's just it won't just be a rotation, it will be a rotation and dilation. So let's draw a picture. And let's say it's a red. So let's say I'm not doing numbers. I think we are comfortable with these symbols. So let's say we have this x1 comma y1. You'll meet yes, okay, no problem. So we have this vector v1. What do I mean rotating this vector by vector v2? Let's say v2 is here. Okay, smaller, and let's say it has the following coordinates. Um, Maybe I should just call it v2 and just call it v1, because later on we want to keep the picture good. Can anybody guess maybe or extrapolate by what I mean by rotation of v1 by v2? This is a useful exercise to do maybe. Sometimes you'll have to extrapolate things, meaning. Yes, right. So the vector v2 has two quantities, right? The vector v2 has an angle and it has a magnitude. It has a theta and it has a magnitude, just keeping it like this. Okay. And we want to rotate v1. So I will not directly say angle is getting added, though that's exactly what happens. But rotate v1 by an angle theta. Okay. And multiply its magnitude by the magnitude of v2. So it's a rotation and a dilation. It's a rotation and a dilation. Yeah, some interesting Euclidean geometry questions are popping up, but we will see later on that. Today we just want to keep it theoretical. And we want to know where this goes. Now, certainly, I think all of you can find where it goes eventually. Even if you don't know a formula for it directly, you can still find it. And if you might even know formulas, but that's beyond the point. More than that, we want to understand. So just removing this part, but yeah. Yeah. So we have this sense of distance. We have the sense of distance, obviously, and we have this sense of angles. The sense of angles, right? So this we want to understand the question I just said, rotating v1 by v2. We can sort of also understand as v2 acting on v1. So yes, this can also be said in terms of group actions, okay? Because the complex numbers are a group in the multiplicative part of it, at least without the zero. But the point is that every vector v2, okay, is sort of acting on v1 and giving you a third vector, right? So v2 is getting, so this action we will denote by this symbol. One second. Yeah. So this action of v2 on v1 we will denote by this symbol star. Okay. Okay, and this will again be in the complex plane. So what is the v2 doing? Let's understand it here. Okay, v2 is acting on C. So v2 is taking every vector in C to a different place, right? It's taking every vector in C and rotating it by theta and magnifying it by the magnitude of v2. That's what v2 is doing. So this symbol that we have, the symbol star, right? We want to understand it. I mean, the symbol star is sort of a new kind of multiplication. It's a new kind of multiplication. Okay, star is a new. Of course, it's not new, because if you know complex multiplication, you know that this is exactly complex multiplication. But we want to see how one can be led to discover it. Okay, the star, because many things in mathematics run in parallel to this. For example, you remember, just giving an example, you have a system of equations, right? You want to solve that system of equations. What do? you you swap some equations, you take an equation, multiply it with another, add it with another, sorry, equation, and so on. You do these operations on the system of equations and you get new systems, right? But then what did we see? So this operation is a very desirable thing, but then we wanted to interpret that as a multiplication, and we saw that this operations can be interpreted as matrix multiplication, and that was very useful for us in the end, right? We were able to find inverse of matrices with that. So we want to understand these things through operations, or through the operations that we know, like break it down in terms of matrix multiplication, which is again broken down in terms of just multiplying numbers, adding numbers in the usual sense. Okay, so that's again what we want to do. We have a new operation, we want to break it down into something that we already know, or at least it looks so that it looks like that by minimal changes. That's what you want to do. So this is a new operation. So you can see that already this leads to a sort of already this is a multiplication. I mean, even if you don't know, even if you don't computationally try to figure out, or maybe you don't need to figure out, okay, what this is, what this v2 v1 and v2 product exactly is in terms of x1 y1 and x2 y2. Even if you don't figure that out, you know that this is a multiplication you've introduced on R2, right? Yeah, which was just necessary. So we have some sort of a product on R2, okay, and this is not an inner product, but this is what is also known as a bilinear form, because this product will be bilinear in the sense that it will be it will be distributive. So it's a product that is distributive. And how are we getting to it? We are getting to it through angles. So see, whenever we have this sense of angles, we have this sense of product. Okay, and whenever we have a sense of product on two vector spaces, we have some sense of angles on those two vector spaces. And this we had seen when we were doing Cauchy-Schwarz, right? We had a sort of product on two vectors in Rn, right? We had a product on two vectors in Rn that was a dot product on two vectors in Rn, and then we sort of made an interpretation of angles in that space. And so basically we define cos theta to be in terms of those distance and products. And also we see here that whenever you have a sense of angles, we have a sense of product, and these things in a product, and these things are bilinear form. These things are rigorous. They can be made rigorous in linear algebra. Okay, some polarization identity and so on. But that's a different aspect of it. So now coming to this, star is a new operation. We are in need of a new operation, and well, we all know what that is. Yeah, so yeah, I mean, we already know it. But even if you didn't know it, you can, by geometry, you can always find this point. You can always find this point. Let's call it v3. You can always find this point by geometry, some angles, whatever, cos. You can use any number of things and do it. Okay, right. Okay. And you've seen that this interpretation of rotation already helps you in simple complex number problems. But of course, we're not going to do that. So this needs to go theoretical and to reach analysis on complex numbers. This, and we know this thing. So since all of us know, so I'll just write it. And in case you don't know, you can just try to prove it later on. It's just a geometry kind of question. Some angles. Yeah. So we do this, and then we have the cross. Okay. This can also be understood in terms of matrix multiplication, but that will not do. In fact, matrix multiplications are the only way to go about it when you are in higher dimensions. Right. So we have a multiplication on R2. Okay. So we see this multiplication is useful. Okay. Right. Now, can anybody try to explain how does I come in the picture from here? How does the number I come in? So the star is a binary operation from C to C to C. Now, before anything, this kind, so knowing that complex, even if you have never thought about complex multiplication like this, it's useful, because a lot of times in a lot of problems, they will just give you the multiplication like this, or maybe in some other twisted form. Okay, maybe they will make this plus and make this minus. So then you have to understood that this is z1 times z2 times I or something like that. Okay, so it's very good to go from unknown binary operations to very known binary operations. There are many. I'll send you some problems like that. I remember, I think me and Noel were also doing once some very strangely defined binary operation would be some sort of division. So this is good to simplify a complicated looking operation. But yeah, this is one way to see it. This you can probably spot anyways. I mean, if you don't, then that's bad luck. Yeah. So how does I come in the picture? Or why is desirable here? So uh, it will take some time to if I go in the very details of it, which I think is not very important. But my point, one thing that I will say from here is that look, this multiplication is good. We have a multiplication which came naturally, number one, and number two is that we understand this computationally, means we know what the answer is, but still this doesn't seem to be related with the usual multiplication we have, the way distributive law and so on doesn't seem to be very related, right? So that's where we bring in the I, right? So you can all understand, right? If I write, so again, this can be explained in a better way by defining I as something 0 comma, I mean, I will be 0 comma 1, right? But I'm just cutting that short a little bit because this is a very very well known point, this thing, in the sense that we are compatible with it, will not maybe be much useful for us. So this is what we do, right? We replace it with this, sorry. So at this point, we are trying to make this operation look more natural. So we replace it with this, with the condition that I is a number whose square is -1. Okay, and that's all. We don't need to show existence or anything, right? It's just what it is. And now when you do this, then you can understand that if you multiply this in the usual way, if you multiply this in the usual way using the distributivity, you get exactly what you should get, and you will get exactly this plus I, which is this product. So you see these two products are isomorphic, but even if they don't, you can already see the similarity, right? See, the second coordinate is been taken care by the I part. Okay, yeah. I mean, you can attach more familiar concepts with it if you can think of them, but this is the thing. Okay enough. Yeah. I mean, you can think your coordinates. Yeah, this, right? So we have this sense of multiplication. Okay. So now we have multiplication on R2, but it doesn't stop there. What should be next? Yeah, just give me 1 second and drink some water. Okay. So before saying what's next, see, the general thing what we are doing here is we are introducing an operation which is geometrically motivated or combinatorially motivated, in this case geometrically motivated, and we're trying to see it through algebra. Yeah, this is a general concept. It can be very good in important constructions if you have to make any. Just like you see in the graph thing also, when we were doing once the proof of the degree thing, that right, if two graphs have the same degree sequence, then you can go from one to the other, right? And there also we had those swaps that we were making, kind of switches that rather we were making, and we kind of interpreted them as operations. And once we did that, we saw that they were reversible and so on, and that was critical in the proof, the reversibility, right? And so if you don't see it through an operation, maybe you won't notice it. And so it's good to again see that through. But again, there the group structure was complicated and not very useful, I think. But in this case, it's critical. Yeah. I mean, you can do your entire complex numbers without I. You can just do the entire complex numbers with this, but you'll always have to get used to this, then maybe I should say. Yeah. And this is much more what we have been, what we do in elementary maths, right? But what is the next thing? So we have the complex numbers, we have a sort of multiplication, okay, and it has all the good multiplication properties, so not going into that. But what is the next thing? Yeah, the next thing is that this multiplication has an identity. This multiplication has an identity. So this multiplication, maybe at this point, I'll just call this multiplication star. Okay, it's good. It's good to get because binary operations questions, they will always, the operation in the end will always be something familiar, but they'll always introduce it as something unfamiliar. That is the whole point of the problems. So a star is the operation, and a star has a multiplicative identity. And needless to say, it's very. Can just someone say what is a multiplicative identity? Yeah, what exactly in this case? 1 comma 0, right? Yeah, because if you just look at the rotation, I mean, you don't have to, I mean, you can solve the equation, you can solve this equation and also figure out what is the identity. So you would have something which gives x1 y1 as the answer, and you can figure out it's 1 comma 0. But even if you look at the rotation the origin of it, you will know that it's just 1 comma 0, right? Has multiplicative identity 1 comma 0. Okay, and it also has a multiplicative inverse. Okay, I mean, every element has multiplicative inverse except for 0, and this you can just try to figure out the reason. I mean, of course, you can find out the multiplicative inverse by actually, what I mean is that you can algebraically, non-insightfully, maybe find out the multiplicative inverse. So let's say x2 comma y2 is your proposed multiplicative inverse, and you can always find out because you want this product to be this, and so you can do some equations and so on, and it's easy. You can figure it out. But even through rotation, you can understand, right? The rotation has a lot of malleability. You can go anywhere to anywhere. So every, why did I say elementary? What was I thinking? Every element has inverse, multiplicative inverse, of course. Additive inverse is obviously there. That's there in R2 also. Multiplicative inverse. Okay. So maybe looking back, I should call this a binary operation introduction of complex numbers. Good to see. It's good to see because you will have other sorts of number systems, maybe quaternions and so on later on. And yeah, right. So yeah. Okay. Now I would like to next introduce the complex numbers in a completely different way that looks completely different to start with, and in some sense it is. It's much more, I feel, much more powerful. Is algebraic. I should call this modular arithmetic. So again, this would be good uh, amalgamation of the concept of polynomials with complex numbers, or maybe in modular arithmetic polynomials. Yeah, we'll see. Polynomials will come in. Basically, modular arithmetic on polynomials gives you the complex numbers. Okay, modular arithmetic on polynomials. Yeah. Okay. By the way, I forgot to say what we did before was it has inverse and everything, so it is what is known as a field. Okay, but again, that's not probably not important. So complex numbers via modular arithmetic on polynomials. Let's try to understand what this is. Right. So what is it? Let's see. So when we let's do the let's give an example of an actual number system that you can make um, through modular arithmetic on just z. Let's give an example there, and then it will be, we can see the parallel better. Yeah. So let's say you start with z. So this is a dummy example, just to be able to relate. So we start with the integers. Consider yeah, consider a remainder by anything, doesn't matter. Let's say by 13. when you do this, then your set of integers gets partitioned into classes, right? Because now when you're only interested in the remainder, then 0 becomes same as 13, same as 26, and so on and so on. Similarly, 1 becomes same as 14, 27, and so on and so on. Okay? And similarly, you have the class of 2 and so on. You have 13 classes like this, right? So we are only looking at the classes, the equivalence classes. What do we do next? Now, if I mean, I'm not going to explain the practical this is we all understand that sometimes we are only interested in the remainder, right? And then it's good to have a arithmetic again, a combinatorial thing. We're only interested in the remainder or number theoretic thing, but again, we want to have an arithmetic operation that is catered towards giving us those things and not focusing on the things that we don't need. Basically, we want an operational view. So now, if you are only interested in the remainders, right? If you're only interested in the remainders, yeah, so the way I should say it is that, okay, we want to do arithmetic. We want to do arithmetic on the classes, on the classes, okay? Meaning that we want to take two classes and be able to add it and so on. Okay? So basically, we have we want a system of multiplying and so on. Okay. So how does it go? I mean, just simple example would be, let's say you have 4 and 5, okay, and you want to do an arithmetic of addition is okay. Let's just do addition first. Yeah, I should do addition first. So this is not the usual addition. Yeah, means yeah, it is, let's say you're doing 4 and 11. How do you add it? You add it and then you take the remainder, meaning that you take the canonical member of the class. You write it in the so that you have a unique answer, and then you write it as 2. And then yeah, so now you have an operation. What is the operation on? The operation then you get is on this set from 1 to 12, and you understand the addition is modulo something, the multiplication is modulo, again the addition is modulo 13, the multiplication is also modulo 13, and that way you are able to do an arithmetic on this. Okay, and on that arithmetic you would know what the additive identity is 0, the multiplicative identity is 1. You even have inverses because 13 is a prime number, and so on. So now you're seeing this remainder process and everything as, again, something which has like a field structure, has a inverse and so on, and that view can be useful. I mean, it is useful. I mean, problems. Yeah. Right. Now we want to see, yeah. Yeah. So a field is a set. Yeah. A field basically just a name that we give to a set which has not one but two binary operations. I mean, this plus and multiplication could be to just two binary operations. Just like here, the addition and multiplication are not the usual addition and multiplication, but addition and multiplication done modulo 13. Okay, such that uh, additive identity, we have additive identity, we have multiplicative identity, and we have inverse. Both multiplicative and additive inverse, other than 0, the element 0. Yeah. Okay. The complex numbers, this also has, and so on. Yeah. That's field is just a name. You need not yeah, know it, but it's good to have names, one name, right? So now we want to understand the complex numbers in a similar way. So I mean, how do you do complex multiplication? Okay. Just if you look at it closely, we sort of, whatever I said, we multiply in the usual way, but then we use this identity that I square plus 1 is 0. Yes, that's W. Yeah. We multiply in the usual way, but then we use the identity that I square plus 1 is 0. Yeah, so it is almost like, now maybe if I think of it, I should do like this. It's almost like multiplying two polynomials. If I replace the I by a variable, let's say x, and this kind of construction is done in a lot of places. If I go modulo instead of x square plus 1, some other irreducible polynomial still. So it's just like multiplying two polynomials, but we are taking the remainder modulo x square plus 1. Do you see the parallel? So you just multiply it like the usual way, x square y1z and x w1 y1 plus x x1z. You have multiplied it just like polynomials, putting it like that, and then you are basically, this next thing is remainder when divided by x square plus 1. How do you find the remainder of something divided by x square plus 1? Just put x square equal to minus, or just put x equal to I, right? I mean, that's the symbol you introduce, right? I mean, that's can I say it in a different way? So certainly you put x square equal to minus 1. So basically, see, you want to find the remainder when this quantity is divided by x square plus 1. Okay, let's forget about I altogether. That's what I was thinking of. Yeah, let's forget about I altogether. Just try to find the remainder of this when this is divided by x square plus 1. Yeah, let's be very naive and try it. A very naive way. Yes, right, exactly. Yeah, you want to find the remainder of this expression when divided. So you sense that that part is good. So you do it, and so you now you see. Yeah, you can use remainder. That's right. You can do anyway, but yeah, this is the easier. Like, this is very nice. Just add and subtract, and this can be used. Good trick as well. But yeah, so you have the y1z. Okay. Now, in our world where we are only concerned with the remainder, we can forget about the x square plus 1 term, because that's why we did it. So what do we get? So you see, this again mirrors, and again, so nothing is name by name happening as it was happening in complex numbers, but there's a parallel, like absolute parallel. There's just a consistent renaming system that is taking us from this multiplied modulo x square plus 1 on polynomials and to the complex numbers. Right? Right. Right. So this is what it is, and yeah, this. Now you will notice that this is exactly what complex multiplication is. If you look at the first line, or if you look at this, and you look at this answer, this is exactly complex multiplication. Just x is replaced by I. Okay. Right. But we can say this. We can say this thing. Why do we need to? Yeah, we can say this thing, and we should say this thing in more concretely, more rigorously, I should say, not concretely, more rigorously, and that is because we just started with a set, right? This all linear polynomials and just multiplying them, right? But you can start with any polynomial and do the same thing. That is the point. So again, just like I was saying, start with z, I now say start with complex. See, this is also, I mean, so it is like we are starting with the polynomials and we are putting the relation x square equal to minus 1. Okay, so we are starting with a free thing where there are no relations. In polynomials, there are no relations, right? A polynomial is 0 if and only if coefficient 0. There's no, like, it can't become 0 coincident by some coincidence. Right. So we start with this, and we do arithmetic on remainders modulo x square plus 1. What do I mean? Again, you have the set of all complex polynomials, and you take the various remainders. Now, of course, this will be an infinite, even the set of remainders is infinite here. What will a remainder be? Remainders will just be linear polynomials. Right? So every class which is a remainder, every class here is a remainder. Okay. First of all, let's see. You have 0, x square plus 1, x square plus 1 square, and many things. I mean, so in short, I can say x square plus 1 times px, or maybe pz will be better, but yeah, that's that class which is all multiples of x square plus 1. Yeah. Then you give me any linear polynomial that can be the remainder, right? So you have ax plus b, and then you have the entire class, all the polynomials which give remainder ax plus b when divided by cx. Okay. This construction is useful because you're starting with a very nice set. This is a nice set. This is a ring. It's a nice set, meaning I mean you can add, you can multiply, yeah, you can divide, and this operation that we are doing, this will allow us to now divide also. We'll see, of course you know it because this is mirroring the complex number, so maybe you know it, that it will, you know it, that it will divide. I mean, you can, if I give you this polynomial, you can do this in complex numbers and find the inverse, and you can tell me what w1 and z1 should be, and then I will have to give it to you that you have proved that inverses exist. Right. But to show it more not rigorously, but to show it in a more non-computational way, in a way that will generalize to other places, will be good, and that can again be given as problems, um, binary operations on polynomials. Again, maybe I'll just give you one or two later on. So what will be the other? So let's come back to this. What will be the class whose remainder is this ax plus b? Yeah, this will be just all the polynomials which will look like this. I mean, right? All polynomials would look like this. There's a, you divide by x square plus 1, there's a quotient, and the remainder is x plus b. And similarly, you know that different ax plus b's will give you different classes. Okay. So each class is a remainder. Each class, yeah, represents a remainder. Now you do multiplication on the classes, you do addition on the classes, modulo that remainder. Modulo the remainder, and you get your complex numbers. Okay. But let us, so as I promised, let us try to understand the inverse, existence of inverse in this language of polynomials only, because that can give us new tools in problem solving, as well as understanding complex numbers from an algebraic perspective. So if I start with a polynomial, so I mean, so my point is that given any polynomial, start with polynomial, let's say px only, polynomial px. Okay. This will belong to some class. Okay, so when I say px, I am representing the class px. Okay. Start with the polynomial px that represents the class px, and find its inverse, or show the inverse exists, or so on. And we will see the inverse. My point is that the inverse doesn't depend on this polynomial x square plus 1 only. It depends on the fact that the polynomial is irreducible in the oh, hold on. I have made a very big mistake. Okay, I'm sorry. This should be r. It should be r. If you start with c, then the I is already there. Right? Then there's not much to do. Okay, and then that will not make much sense. Yeah, then it doesn't make sense. Then you will not get inverses. So let's not be a, sorry. You have to start with the reals, because obviously you're trying to define complex numbers. Find its inverse. Okay. in this new operation. In this new operation. So what do I mean? So basically, we want to find a qx. Yeah. At the core, that was the problem. Yes. At the core, that was the problem. But even before that, I mean, I'm trying to define complex numbers. So starting with cx doesn't make any sense, right? Yeah, but then you won't know why. Maybe it's hard to see why it not being irreducible doesn't imply inverses. That's not completely clear, is it? So that's in the end a good reason, but in the beginning, yeah. But you can still, I mean, you can still take complex and you can do this quotienting. You can take the set of remainders and you can do addition and multiplication on them. There's no problem in that. Okay, but that will not give you anything. That will just give you the complex numbers back. But that is hard to prove. I will. That's not hard to prove, but that's probably, yeah. So my point is that if you do this and then you take the remainders of this when divided by x square plus 1 and you take the classes and you do multiplication on that, this set you are going to get will be c again in some sense, because yeah, but probably not very useful. Yes, I don't think, if you've not done group theory, you won't understand, and there's no need at all to understand that right now. So we have this px. Okay? We want to find the qx. Okay, you want to find the qx such that this is 1 in this world. Okay, and what does that mean? That this is equal to 1 modulo x square plus 1. Does everybody see the point? Because that is what this multiplication is about. Right? Now, let's break it down further. It means that this px times qx. So maybe I should just not rush too much. I'm trying to say that this equal to 1 implies, or means rather, means is not even implies or anything, sorry. This means that you're doing the usual multiplication, right? That's what it means, right? You do the multiplication and then you end up in the class. You end up in the class of 1. The 1 is class somewhere here where we have 1, we have x squared plus 2. Those things that leave remainder 1, right? You should end up in that class. Now, what does it mean that this should give the remainder the same as 1? As 1 gives when divided by x squared plus 1, which means it just gives remainder 1. Right? Mod x squared plus 1. Okay. This, by definition, again means that px qx minus 1 should be divisible by x squared plus 1, right? So this should be x squared plus 1 times, let's just call it a tx. So given a polynomial px, we want to find a qx and maybe a tx also that satisfies this equation. Okay, so we want to find, that should be said here. I should have said that in the beginning. I want to find px, sorry, find a qx and tx that satisfies this. This is a problem in polynomial algebra. And it is true that you can find such a polynomial. Unless, so when can anybody tell me when can you not find such a, what is the exception? I'm sorry, just give me 1 second. I have to close something. Yeah, exactly. No, but yeah, px of pfx is identically equal to 0 or it is in the class of 0, right? If it's a multiplication, if it's a multiple, if px is a multiple of x squared plus 1, then there's no hope of getting 1 in the end, right? So exception is the class of 0. So yeah, just exception is 0. Other than that, you can always find what is the explanation of that. Yeah, anyone? Right. Uh-huh. Okay. Uh-huh. So, sorry, are you going to use complex multiplication in the end? I and so on? Okay, that's fine. But yeah, that's a perfect way to do it. In fact, that's a good application of complex numbers in polynomial algebra. But I want to go in the reverse way. I want to find the answer to this without using complex numbers. I want to construct complex numbers because in your tests, in your to understand this thing in general, what happens is that what if I tomorrow I replace the x square plus one by x to the power 4 plus x square minus 1. My claim is you can still find such a px. Okay, and now you'll have to prove this or you have to find this in a different way. Now complex numbers will not be so helpful. Okay, so that will be another place where inverses will exist. Okay, all this can be said in one or two lines using college algebra that you are quotienting by a maximal ideal, but this is the understanding of that. In fact, this should come first to understand that, to relate to that later. So we want to say this without using complex numbers. Okay? But this is a perfect way to approach. This is a perfectly legal way to approach it. I mean, tomorrow if you have some other this like this, and you can still do something like what you said. You have a linear. You can go to that linear and you can try to find it using your um, ad hoc methods. Maybe I can say then. But how do we do it in general? Hmm. So this can be said in many ways, but I think again the best way is to do this just by, I mean, the simplest way rather maybe, most elementary way would be just mimic the proof of the corresponding statement for integers. Right? What is a statement? If a and b are coprime, then there exists an x and y such that, I mean, integers. Yeah, we know this. Does everybody know this? This is the first question. Otherwise, it's difficult to maybe think of the idea for the polynomial case. Anyone who does not know this, that given a and b, because we can then just run the proof, that's important. So, given two integers a and b, you can always find out x and y in integers such that the linear combination is 1. Basically, using a and b, you can generate everything. Because once you can get 1, you can get anything, right? So when a and b are co-prime, then it's like they don't share any common factor, right? So you can get more and more things. They are not bounded by, they are not restricted by, don't have the responsibility of being the multiple of something always because they don't have a common factor. So they can like go everywhere. I mean, yeah, that's it's just a way to say it. Okay, so we know what that is. So we can use the same technique here, the exact same technique. Yeah. X square plus 1 is an irreducible polynomial. Now, what does that mean? It means that if GCD means, you can just think of GCD as common roots. but it's much more than. It has more interesting consequences, not just common roots. But let's say that if the GCD of two polynomials, these two polynomials will always be 1. It doesn't share a factor. No other polynomial can share a factor x square plus 1. Sorry, can share a factor with x square plus 1 other than being a multiple of x square plus 1. That is exactly the statement that if it has I as a root, then it should have minus I also as a root. Those two roots come in the pair symmetry. So the GCD has to always be 1. GCD has to always be 1 because we are assuming that we are assuming that x square plus 1 does not divide px. GCD is 1. Now you can run the proof of the Euclidean algorithm. Okay, I will leave that part because it's something we should try first. Okay. Right. It can be done in other ways also, but this is okay to do. It's good to do. And in the end, what do you see? That you can start, you could have, instead of x square plus 1, you could have done this thing starting with any irreducible polynomial. Yeah? Because if it's irreducible polynomial, right? If p1x is irreducible, means it's like a prime, right? Then either p1x will divide px, meaning that all the roots of p1x are there with px, or the GCD will be 1. Okay? Only these two are the cases. Yeah, at least intuitively you can understand. This is not hard to put. Just think about it. I have not done polynomials formally with all of you, but just think about it. It's basically you can't break up p1x into two parts. Either you give all its factors or you don't give anything. Right? And you can do the same construction. Now this can be good, can be useful construction to do. If we give you some other polynomial, to rough you up, you don't. Yeah, draft. All right. So next what? So we have understood complex multiplication from different complex numbers from different angles. Right. Next, what we will do. So not today. That's it for today. I think from the theory part is we will look at complex functions. Okay, and we'll try to see how we can interpret the notion of limits there, notion of complex functions there. Okay, of course, in parallel, I will do some interesting some applications also of these things in problem solving. Especially some of the harder questions in Olympiads need these things, but also, anyways, yeah, we'll do that. But the theoretical part will be we'll try to understand how to look at infinitely many complex numbers at a time and how to make what all we can do with them. That's basically the first key. And then the techniques of derivatives which we have, we'll also try to see the parallels there and the non-parallels and so on. And yeah, that goes on. Yeah. So I think that's it for this part. Now I want to move to some problem solving. Okay. So basically, I want to do some problems which I've sent earlier. So yeah. Any preferences? Any problem that you people want me to do first, which I have shared with you people? No? Okay, then, yeah. The rate of convergence of a sequence. See, it can have, I don't know if there is a standard. Is there a standard definition? Right. See, I believe there will be several ways to define the rate of convergence of a sequence. Right. I believe there will be several ways. This usually is a topic that is a part of numerical analysis, right? Which I have not studied. But the point is that rate of convergence. Rate of convergence. So let's say you have a sequence xn that is converging to L, and you want to see how fast it is converging. Right? So maybe then you can study this compared to maybe the previous one. You can find the ratio of this limit. This can tell you, right? This the ratio of this limit can tell you how fast it is converging. That can be one definition. Or I mean, usually there will be two different things which you want to compare, and then you can just take the ratios and you can find the limit. Root over. Okay. Oh, so then they should define the definition of rate of convergence. Okay, I don't know that there is I don't even know if there is a universal there are hundreds of definitions. I think they should give a definition and then you can easily find using that definition. So don't worry about this too much. If they ever give you this, they will tell you what they mean. Unless you're taking a numerical analysis course where they have defined it in some way, then it's okay. But I don't think there is a universal definition. Yeah, yeah, but if they tell you the definition, you can obviously find it if you just plug it in. The main part would be to find the limit, which you can also do. Yeah. Right. Let's do one problem which has the complex number flavor. But of course, this is nothing what we will do. We'll do more of the infinite many complex numbers we'll deal with, and so on. But this is one question. So this I had sent. So fx be a polynomial. Should I just no? But then I cannot write. Yeah, fx be a polynomial with real coefficient. So fx is in Rx. So I think I have done one side of this. Other side I need to think as well. Okay. So let's do one side. Okay. So if first, so if the roots of fx are all real, so it has all real roots. Okay. Then f square x cannot be written. So f square x means here the square, okay? not composition. Cannot be written as, and this is one version I believe. So this one of you had sent me, but this is on simpler version I believe of many other interesting questions of this type. Sum of squares and so on are interesting topics anyways. For some g, just say g and h in Rx, real polynomials. Yeah. So let's do this first, maybe. Did I send? Oh yeah, sure, yes. Means in the evening, which I want to send, means whatever. Yeah, the complex, that was also complex number, right? Okay. I also try that. Yeah. Okay. This one, have you tried this one? Have you done this one? Let's see. All the roots are real. Then it cannot be written. So the way you will do it is maybe assume it can be written, right? So if yeah, that's the only way to, rather in some sense, because if it can be written, then not all roots are real. Right? Then not, I mean, then fx has non-real root. Then fx has non. I think I am to try this myself. Yeah, non-real. I think I've done the other side. Has non-real root. So let's write it. So let's write it. Yes. What can we do now? Yeah. Okay. That's interesting. How? Right. Yeah. Okay. If is it a real root or is it? Okay. Very good. Yeah, I think you are there. Yeah, fx alpha is real. Good, good. Yeah, it's easy. So I think more also same idea. So this is easy, right? Yeah, like this, and this is positive. Yeah, right. Very good. So every root of fx square should be a root of g square and. Yeah. I mean, done. I mean, when I say this can be written, I mean in a non-trivial way, meaning that it's some, not just yeah. I mean, yeah, the degree has to be different. Yeah. Right. So the degree of all three cannot be same. Yeah. So this is a clear contradiction. Yeah, that this is good. I think the way I was just thinking now is if I do like this, then also maybe I was getting something. This, and then I was assuming that they don't have any roots in common. Um, will that yeah, so that you can assume, right? Because if two of them have a root in common, the third has, so they are all like pairwise coprime. Okay, then you have this thing, right? F minus g also must be a square, and f plus g must also be a square, and there you get that f is a square, right? You get something much more stronger. I mean, you get that um, f has all roots complex. Okay, but of course there is a catch to it. Has all roots. Yeah, all roots complex. But this is under the assumption that they are coprime. So if they are coprime, if f, g, and h are coprime, then f has all roots complex. Okay, right. Yeah, and this is precisely the same thing. If there is a real root, then it is then that they are common. Yes. Yeah. So last part is, so you write f minus, so the product of two things is a perfect square, right? And f minus g and f plus g will be coprime. So okay, this I have to say. So if f and g, yeah, I didn't say this. If f and g are coprime, means there's no common root, then there is no common root between f minus g and f plus g. This is, you can check, because you can say if there's a common root, then it will divide the sum, it will divide f, it will divide g, right? So I'm using this. Okay, try to show this. This is not hard. Yeah, and so each of them has to be a perfect square, right? Because if the two things are coprime, then any roots that are coming two times, that has to be entirely in f minus g or entirely, right? If any root, so if h has alpha as a root and beta as a root, and if alpha is coming twice, both the times it has to be a root of f minus g, right? So both have to be perfect squares, and this is what we know for numbers also, right? So these are some. This is basically, I'm just trying to mimic the thing for numbers. That's my proof is more like that, more algebraic, and this proof is more analytic. Yeah. So, anyways, Yeah, so then you get f is a sum of two squares, so it means that it cannot have any real root. But again, I have assumed the coprimality, which is also a good thing. It's like, reminds me of Pythagoras and the proof. So if you try to do the proof of Pythagoras, finding all the Pythagorean triplets, finding all the Pythagorean triplets, finding all the Pythagorean triplets of this, solutions of this where a b and g, a b c are coprime, find all solutions, right? And you can express all the solutions in terms of some t, right? It's not t. You will need two variables, of course. Yeah, parameters, and the proof goes exactly. I mean, one of the proofs goes exactly like this. Okay. Anyways, so this is basically my idea came from there. Anyways, so this is simple. How do you do the other direction of this? So the other direction is f has if f has non-real complex root, then f square x can be written again in a non-trivial way as sum of the squares. F square can be written as sum of the squares. Sum of the squares of two real polynomials. I've seen many extensions of this question, this kind of question. How do you express things as sum of squares? And when you can express things as sum of squares is in general a very good question, a very important, interesting question. It's a very interesting question. Even like which numbers can be represented as sum of squares and how do you describe all of them, so on. It's also an interesting question. This is for polynomials. Let me think about it. Yeah, so in today's class also we looked at sum of squares, right? Something like this. So f is a real polynomial. Okay, any ideas? How do you get sum of squares? So let's think about it, right? I mean, forget about the real roots for a second. If you have a root like this, and you may have factors like z and z, x plus z and x plus z bar, how do you write it as sum of squares? I mean, of polynomials. In the same way, right? In the same way as you write x plus I and x minus I, same way. Like this, and you see you get a sum of squares. I'm surprised nobody thought of this. Okay. All right. Finish the problem. Now the rest of the problem is simple. Okay. Because f square is the roots will come in squares and so on. This is all to get the splitting going on. Yeah. Okay. Finish the problem for me. Yeah, let's go to the other question we had. Can I copy paste or something? Yes. Yeah. Hmm. Yeah, yeah. Yeah. So if z is a root, then z conjugate is also a root, right? That's why I mentioned once in the middle. Yeah, it's a real polynomial. I mean, if it's not a real polynomial, then this is not true. For a real polynomial, this is true, right? Right. So I think that is fine. Yeah. The question I sent today, right? So again, one of you had sent me today only. So z to the power k equals 1. So these are collecting the roots of unity for different case. And then we are saying that any for any m and n, okay, where the situation is like this, m is less than n, we have u1 union u2 and so on. So basically you can go till m. You can go till any point. So the idea is that, okay, not the idea, but point is that this is m, and then this is, you can collect the roots from 1 to m, and this will be contained in, you take another contiguous string of length m. Okay, take another contiguous string of length m, which is ending at n, but then that's really arbitrary. You can just take another contiguous string that of length n, length m, and that's good enough. Then this roots will be contained in that. That is basically the statement. So you understand, right? This n is not the thing. Yeah, maybe I shouldn't say more. Let's think about this, and let me also think. Yeah. So, okay, again, once again, is the question not clear to anyone? Yeah. So we have these roots of unity. The roots of unity for z equal to 1, for z square equal to 1, for z to the power k equal to 1. So they're saying that you collect the roots of unity from z equal to 1 up till z to the power m equal to 1. Okay. So these are the roots of this, and roots of this. So we have m polynomials like this, next, will come one after the other, and you collect all their roots. So you have m of them. Now they're saying that you have m of these in a line, in m consecutive, The thing is that if you take any other m consecutive numbers and take their roots of unity, right? If you take any other yeah, then the roots of the first m will be a subset. Of course, it will not be equal because these have much more roots, the bigger numbers. Yes, yes, please. Yeah. Hmm. Okay. UK is a subset of. So you're saying in general. Can you just explain us this in, yeah, why? Can you explain it? Hmm. Exactly. Okay. Right. Yes, that's good. Yeah. Right. Okay. 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 So okay. Can anybody expand on that? Let's. So that's okay. That's correct. But for any j, I just want someone else to maybe expand on this. I think you have got the proof. Yeah. For any j in 1 to m, let me see. Let's see if others have got it. Or yeah. Okay. That's fine. That's good. Yeah. Okay. No. Union will give the right. You sure you're not going to get anything more? Yeah, that's right. Should not get anything more. Okay, but anyways, go on. Yeah. So why is it contained in the right hand side? Yeah, but you can maybe complete it. And the way Chopin has said is also because this any number j from 1 to m, it will have a multiple in any m consecutive numbers, right? That's what I was stressing in the beginning. There's just m consecutive numbers. Yeah, it's done, right? Yeah. So can you is it does it follow from your technique also? Maybe a good way to see. Not that I can see, but yeah, maybe I mean this is what you're saying is true. Maybe it's true, but you'll have to prove it. You'll have to go by this only, the other method to prove this. But yeah, it's all the same, right? So this is more about divisibility. Okay, more about divisibility. That if you take n consecutive numbers, then it will contain a multiple of n minus one, n minus two, and so on, right? Because the multiples of n minus k, for example, they take jumps of n minus k, so you can't jump across a string of length n. So I guess that's fine. Yeah. So we did these problems with the complex number flavor. um, yeah, let's stop here today. Okay, you can do more problems, but yeah, then it will be different flavor. Let's stop here today. We can continue next time. It's fine. um, yeah, yeah, let's do that. Okay. All right. Okay then. So that's it for today. Yeah. 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 So if you look at Stein Shakarchi's book on complex analysis, they really just the starting is they define complex numbers, they define the multiplication, distance, and so on. And so that's basically what I did today. And next time I'll do sequences and so on. Yeah, and then distances and so on. And after that, we go into the differentiability and yeah, so on. Yeah, I mean, the polynomial part that I did, that is not useful in complex analysis directly. I've never seen it actually in complex, but that's again a good topic in good application of algebra. Yeah, means complex numbers, it might be useful, meaning that it's useful in the algebra of complex numbers. In the algebraic side, it's looking at the complex numbers as a ring, it is useful. But as in analysis, that quotienting, at least not before you go to something called Riemann surfaces. Maybe it's useful there because there you have to really do some quotienting. But yeah. But anyways, we'll soon pick up. But this was like a review. Okay, sort of. Mock 2, no, I mock 1% right on Sunday, and after that I'll do mock 2 soon. So mock 2 we will have next week. Okay, again. I know I've seen, yeah, yeah, I've seen it. Yeah, I saw one or two questions. And mock 1 I have not yet checked. I've tried to solve it myself. In WhatsApp. Yeah, you had sent me. Yeah, yeah. That those are minor things. That is fine. Maybe if you can correct the LaTeX source and send the PDF again, it would be better. That is same thing, yeah. But they are minor errors. I can correct them while giving the paper. Yeah. Uh, okay then. That's it. That's it for today. Yeah. Thank you. And either ways, Noel, like you don't get hardcore complex analysis to. Okay, yeah, it's there in your syllabus, so we'll obviously do. Yeah, but yeah, but you should learn it anyways. Yeah. Yeah, yeah. Of course, you have to learn it anyways. Yeah. 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 Okay. Yeah. Certainly. Yeah. Okay then. That's it. Thanks. Bye. Bye.